Hello everyone, in this video we'll be looking at how to understand graphs dealing with equilibrium. So in this first example here I have two graphs showing hydrogen iodine either being produced or decomposed. And we're going to talk about what the slopes of these lines mean here in a second, but let's start by writing down equations so we can understand how this all sort of comes together. So let's talk about this left-hand side here first. We can see this green line is increasing and the blue line is decreasing. So we can assume that H2 and I2, hydrogen gas and iodine gas, are our reactants, and as they're consumed, we can see their concentration going down. There's a production or an increase in the hydrogen iodide. So let's write that as our base equation. So we have hydrogen gas, H2, and we'll put in our state symbols as well, plus iodine gas, so I2. Remember, both these are diatomic, which means that they always come together, so H2, I2. Other diatomic gases are things like N2, O2. Okay, so remember they make that little 7 in the right-hand side of the periodic table. And then we know already we're in the equilibrium unit, so I'm going to use this reversible reaction arrow. So one arrow going one way, one arrow going the other. And like we said earlier, our product is Hi, so hydrogen iodine. And that is also a gas. Because remember, if things are not gaseous or in a gas form or aqueous, they cannot be in the equilibrium expression. Okay, we can't deal with solids and liquids when we're dealing with this type of chemistry. So we have these two arrows here. We have a forward and a backwards reaction. I already hinted at this idea that hydrogen iodine is increasing. Okay, it's being produced. So let's call this, let's label this green because it's already green. This is our forward reaction because hydrogen iodine is being produced. So that's actually this part of the arrow. It's our forward reaction. Okay, we're combining hydrogen gas and iodine gas to create a new compound, hydrogen iodide. If I look at this second graph, which I didn't talk about yet, and I look at it really quickly, I can see that, okay, at the start here, this blue line is 0, and it gradually increases, and then it sort of reaches equilibrium. And that equilibrium is H2 and I2. So that's my reactants in this equation. And then if I look up here, I can see that I have hydrogen iodine, and it's being consumed in the process of creating this over here. So this second graph over here, okay, this second graph, oops, I should have done that in blue, sorry. The second graph is my backwards reaction, okay, my reversible reaction. That's why we have these two arrows. I can go forward and backwards. So this reaction here is, let's go back to black, H2 plus I2 goes to Hi, and this side of the equation is Hi goes to H2 and I2. Okay. This is something we would have seen in Science 10 and Physical Science 20, this idea of reactions going one way. When in reality, if we're dealing with something in a closed system that can reach equilibrium, we can introduce this concept of a double arrow. Okay, represents equilibrium, both a forward and reverse reaction. We also talked about it in class in our notes that when these lines start to level off, and they all level off, that is the equilibrium. They've flattened out. They've reached equal concentrations over time, and the forward and reverse reactions are occurring at about the same pace, so we don't see fluctuations in any concentrations. Okay, so that's a pretty intro graph. I know there was a lot of content in there, but I'm not going to spend as much time on the next few graphs. So let's scroll down. We're going to look at this one next. I'll just grab my black again. And on the left-hand side here again, we can see that we have something starting at 0 and it's being produced, okay, that upward positive slope, and it's being produced quite fast, and then it reaches a flat line, so equilibrium. Remember, a flat horizontal line in these types of rates of change graphs represents no rate of change, so there's no change in whatever species this is, so that would be the rate of change of 0, or a slope of 0 if you want to think of it mathematically. And then we have these other two lines up here, the green and red, that start off at a higher concentration and then they go down, which means in chemistry they're being consumed, they're being broken apart. So something like this could be represented as SO2, so sulfur dioxide, reacting with oxygen gas, reaches equilibrium with sulfur trioxide. Okay, and then we could go back and balance this. Right now this is not balanced, and I'm just going to leave it like that for now really quickly because I want to focus on the graph. And then on this side of the equation over here, we have the same thing, but you'll notice that we're looking more so at the reverse reaction because we're starting off with a high concentration of SO3 and it's going down, and then the other two reactants are being produced. So they're going up. They're reaching a higher concentration level. And then eventually, you'll notice here it says equilibrium is reached. All of our lines have flattened out. They all have a zero rate of change. So that means they have a forward and a reverse reaction that are equal to each other, something we cannot perceive. So that is equilibrium again. Okay, so this is looking at 3 species. But what's really important here is to understand how we can start to modify equilibrium or stress the system and then see how the system bounces back to try to reach that initial equilibrium. And that's something that we're going to look at in a future video called Le Chatelier's principle. So let's scroll down here really quick. This is another equation. Let's just assume that we have some reactants and products, and it doesn't matter because they're in equilibrium. And at some point in this reaction, we're dealing with hydrogen gas, so H2. Okay, so we see this big spike here. We see the forward reaction is pretty flat, and then all of a sudden the forward reaction goes up. Okay, so that goes up because we've introduced hydrogen gas. We've injected it into the closed system. And then we start to see that this hydrogen gas is used. Okay, so it starts going down. That's why we see this gradual slope down. And as hydrogen gas is used, well, you know what? That reversible reaction, or the other part of the reaction, it's using the hydrogen gas and going up. And you'll see that the equilibrium is reached again, but it's at a higher concentration. Okay, a higher concentration. So I'm just going to go concentration, and remember square brackets means concentration in chemistry. So we've shifted the concentration of equilibrium from a low value to a high value by introducing something new into our closed system. Equilibrium is still reached because the forward and reverse reactions are equal to each other. We've just shifted the concentration. Okay, so that's something interesting to look at. And then we can look at this in a very detailed system with this last example down here. Okay, in this case, we're looking at, again, 3 species. It's giving off energy. Okay, so it's exothermic. It's giving off energy as this reaction occurs. And we can see that in this section here, let's maybe use the highlighter this time. In this section here, we have equilibrium. Okay, then we can see a change in the system. Okay, and we can see how it sort of reacts and it reaches equilibrium again. Okay, so we have an equilibrium here, and then you can see this huge removal. We can see this CO drop really quickly. And then the system tries to restore itself, and we can see that it starts to replenish. And as it's replenishing, by making more CO, it's also making Cl2. Okay, so we're on this side of the equation. And then the Cl2 goes down. Okay, and then we have another equilibrium system here. We've reached equilibrium again. And then we've modified the equilibrium again by removing a bunch of everything, actually. So we've removed, let's see, we've removed the chlorine gas, we've removed CO, and we've removed COCl2. So this would have been done by maybe releasing pressure on the system and venting some of the gases out. But then again, after you vent the gases, the system will try to reach equilibrium again. Okay, and that equilibrium, while the concentrations may be different, the ratio of the concentrations will always be equivalent because they're based on the KEQ. And that's the important concept around all of these equilibrium pieces that we're going to be looking at, is that KEQ, KEG, KEQ is a ratio. And that's important. All right, I will see you in the next video.